Okay, so welcome to the Parameterized Algorithms course, and yeah, so I hope you hear me well. I mean, we tested it a while ago, but I hope you will hear me well. And yeah, so I want to say that yeah, this course will be given in English because I mean, I think currently in Moodle everyone looks Polish here, but we know that there's at least one participant who is listening to the lectures. She's not attending them, but listening to the lectures, and she's not Polish speaking, so the lecture is in English, and we want to make the videos more accessible to some people afterwards. So that's why we'll be giving it in English, and the slides are in English. Okay. But I'm going to start with some organization thing, Yeah, so there's Moodle. I checked a few minutes ago, and 3 people from USOS didn't register yet for Moodle. So I sent you all the details there, and I mean, you could all the details to register to Moodle. Please register there. We won't be sending much more emails, maybe except for the most important ones at some moment. But we don't plan to generally send emails about everything. The information will appear on Moodle. So this is the main channel of communication. Okay, so please do register. In particular, we have got like there's very long document about rules. How we plan to evaluate you, and this changes a bit since our original plan. Just to adjust to the fact that we are doing it remotely. The first thing we introduce quizzes every week. So after every lecture, there will be a very short quiz. This short quiz isn't very complicated, and you can make them. We can take as many attempts as you want, and it will give you back. There's like the quiz from today lecture is like 5 questions. The quiz will give you feedback how many points you score for each question, and you pass if you get the and I mean you pass the quiz if you get perfect score. Yeah, so the goal is to get a perfect score from the quiz, but you can make an attempt as much as possible. I mean, as many times as possible, so you can like test which question was wrong, think once again, and check. I mean, in the end, you can brute force the quiz, yeah. But the point is that you spend 15 minutes after each lecture on actually like seeing what was there and recalling what we discussed during the lecture. So yeah, so we'll be also experimenting with the format of the quizzes, so the feedback is most welcome. But yes, there is a quiz, and the quiz has deadline by the next lecture. So this requires from you that after every lecture, you actually spend this 15 minutes either thinking or brute forcing the quiz, so you have got contact with the lecture. And this is a mandatory requirement to get access to the first exam session. Yeah, so if you don't pass the quizzes timely, if you don't pass all the quizzes, you won't be allowed to take the exam in the first exam session. I think we wrote something that you can be late by a week with 3 tests. So yeah, so that's the rules. I haven't implemented this yet in Moodle, but I will try to figure out how to do it so that you can be late and somewhat marked. Yeah, so these are quizzes, and these quizzes are supposed to be simple and take you 15-20 minutes. If that won't be the case, please let us know. That I mean, this is like we are learning what's the best format here. Apart from the quizzes, there are homeworks. There will be 5 homeworks, and every homework consists of 3 problems. And each problem, I mean, we aim at having simple, medium, and hard problem at every homework, so that doing every simple, I mean, gives you a reasonable amount of points even doing every simple problem. Yeah, and we announced, I mean, you should already see in Moodle the first homework, which is due to 6th November, I believe. So we expect that you will upload through Moodle your answers. I mean, this can be, I mean, the preferred version is some PDF from LaTeX, but you also can write on sheet of paper, make a photo and send it, and hopefully it will be readable for us. Yeah, so those are the homework. The homeworks will be graded hopefully on time, like during and we'll soon announce the second homework. So because there will be 5 homeworks, there will be overlapping in time a bit. So it won't be that we wait till the end of the first homework to announce the second one. There will be some overlap, but hopefully there will be not that super time consuming, but they're definitely not 15-minute quizzes. And then there's an oral exam that somehow gives you the mark, and your homework, your points from homework, plus the fact if you did the quizzes give you some modificated to the final grade at the end. Yes, so if you don't do the quizzes, you don't have the first exam session, but you also have got some minus in the second exam session if you don't do the quizzes on time. Yeah, so please look at the quizzes and give us feedback how it works, because that's really like sort of a new format for us. Yep. So this is about branching. I think that's about the organization from the grading perspective, from the tutorials. So we also had a very long discussion with Michał and Wojtek about how to make tutorials and what's the best system. And we'll be this will be an experiment. So please give us feedback if anything you think goes wrong or you want to modify something. We will evaluate some way. But our first idea is that will be after every lecture there will be on Moodle published a list of exercises for the tutorials. Wojtek promised me that the first one will appear during the lecture, so I hope by the end of the lecture it will appear on Moodle. And yeah, and there's on Moodle there will at the end of the lecture there will also appear like some random group assignment. So we took all of you, so there were 20 of you in USOS and additionally 3 people like PhD students joining the course that are not in USOS, so there are 23 people. We completely randomly assigned it to 6 groups, so there are 5 groups of 4 people and 1 group of 3 people. And our goal, our intention is that inside these groups, you will discuss between yourself like how to solve these problems or what are your ideas, so that every group will somehow like schedule their own meeting somewhere or like exchange emails. I mean, it's up to you how you discuss between you. So, but this is like supposed to be work group or some discussion between you. And then at the tutorials that will start next week, there's no tutorial today, there's tutorial next week. Wojtek will be discussing with the groups how it went, which was difficult, which was not, and discussing the solutions and the problems during like tutorials on Zoom. But the details of the tutorial meeting will be published by Wojtek later because the tutorial is next week. But the first tutorial is next week. But today we'll announce the first series of exercises for tutorials, and you're supposed to look at them, organize yourself within your group, see how it goes, and then discuss it with Wojtek, discuss the problems with Wojtek next week. Okay, so that's for the tutorials. And yeah, we hope, I mean, if there will be some problems with this format, please let us know. In particular, if there will be like some like unlucky group when there were like I know 2 missing people or something like that, then let us know, then we'll make some reshuffling during the groups. In particular, there are 3 people in USOS that haven't yet registered to Moodle, so if these people will turn out to be like not really participants here, then we'll need to make some reshuffling. Okay, yep, that's all I think I want to say. Michał, do you want to add something to the organization part?
Just wanted to say that about the tutorials, our intention was that you do not spend the whole week on trying the tutorial problems, but just try to arrange a meeting for, I don't know, 1.5 hour, 2 hours within your group, discuss the problems, try to solve as many of them as you can, and we hope that you will be able to participate in the tutorial next week, having already solved, let's say, half of the problems.
Yeah,
that was our intention.
that's a common thing. I mean, in the live tutorials on the previous editions, it was really the case that the list of problems were like 15 problems, and during the tutorials, half of them were solved or touched. So please, I mean, there are like sometimes there will be many problems. Maybe we'll try to make some. No, I mean, we try to evaluate it, but it's not that you should spend like 15 hours per week on doing this fix. Yeah, please.
Yes, so essentially the tutorial will be also about trying to solve together the problems that nobody managed to solve, but everybody managed to have a thought about. Yes, so that you are not bombarded with problems that are completely new through Zoom. So the idea for you is to try to solve as many as possible and get a feeling of all of them, so that then the tutorials are more productive. And you can do it inside your group.
Okay.
Yeah, so one more thing that I wanted to say is that in the evaluation criteria that you have on Zoom, we expect that that the quizzes and the homeworks are individual work. In the coronavirus times, there are many different definitions of individual work. So we try to axiomatize what is individual work in the evaluation criteria. So please look at it, what we consider individual work there. Yeah, I think that's it from me about the rules.
Yeah, I also don't have much to add. Are there any questions? I don't hear any questions. So you can ask questions on chat. I try to follow chat. So yeah, okay. So in Moodle currently, you should see already the first homework, and you should see the first quiz, and you should see actually the PDF with the slides I'm showing you. So that's also there's right there, and at the end of the lecture, there should be some things for the tutorials appearing there, but we'll see how it goes. Okay, so I'm going to go to the more interesting part of the lecture, namely the algorithm, parameterized algorithm.
So I zoom out now. Yeah.
Okay,
So thank you very much. I will be there for the giving the lecture, I think, in 2 weeks. Okay. So bye.
I mean, how? Okay, so I'm going to, I mean, so let's now look at the slides. So there's like me speaking and the second me with the tablets with slides. I hope that's somewhat convenient. I will see. That's the best thing I figured out so far. But there are slides there, and the slides, uh, yeah, and yeah, so these are slides that actually are scrapped from some school we did for in Gdańsk a few years back with Łukasz and Marek and Michał, and there's a Frankenstein of old slides. That's why we are all mentioned here. But yeah, so I'm going to talk today mostly about branching algorithms. We'll see how it's in a minute. That would be very complicated. It's very intuitive thing, but let's go on. Okay. So what we are trying, so that's the slide I was supposed to show at the beginning, but here I want to say that if you need some reference, there's this book that some of us, I mean, me, Michał, and some other people wrote a few years back. I think almost everything we'll say here is in this book, unless there's something very fresh, very new that's a bit after this book was published, but most is in this book. There's a link on the Moodle to the PDF version of this book, so you can download it and look at it. I think our library also have a few copies if you prefer the paper one, but or one or two copies, or maybe actually one copy is okay. I don't know how much
They're
it's
not available.
not
Anyway.
available. Okay, but there's a PDF up there, so I mean, there's a PDF there, so you can use it. But the book, hopefully the PDF version is sufficient for you. Yep. So today we'll be discussing branching, but also like what we are really doing here. What's this parameterized algorithm? What we are doing here? I mean, what's really the motivation here? And what area of algorithm design we are really exploring here? And yeah, so what we are doing here, we are trying to solve problems, and we're mostly focusing on hard problems. So we want to doing like during the like basic algorithms course or something like that. You have got usually we look at polynomial time solvable problems, and you are doing Dijkstra in some near linear time. Then you're doing some flow algorithms and optimizing polynomials in some flow or matching algorithms and this type of problems. Here we want to take one level of hierarchy higher and look mostly at NP-hard problems. So we're looking at problems that where we don't expect the polynomial time algorithm, but we want to solve actually them. And we want to solve them and we want to solve them as quickly as possible. So we don't expect these problems to have a polynomial time algorithm. Yeah, that's the thing that we learned, for example, at the Algorithmica course, that there's some notion of NP hardness, and some problems don't really have. I mean, we don't expect them to have polynomial time fast solutions. So, but we want to understand like, okay, so what can we do with them? And we want to understand in which cases we can solve them quickly, or what are the fast algorithms for them, or how actually like can we measure somehow like which algorithm is better and which algorithm is worse. As we see, there are different exponential time algorithms. There's very rich variety of the exponential time algorithms, and we are trying to somehow classify them or understand how to classify them here. That's a very rough sketch of what we are trying to do here. So that was a very rough, very abstract sketch. So let's do an example. This is like a very like worn off example in this area, but let's go over it since it's introductory course. Let's say that we made some number of measurements, okay, say 10,000 measurements, and with some probability, there's some failure and the measurement is like complete crap, okay? And so we can think of this measurements as nodes of vertices in some graph. And these measurements, I mean, we can compare to measurements and say whether they make sense together or not, whether they're contradictory or not. Yeah. So an edge between two measurements means that they're contradict. I mean, one of them needs to be wrong, one of them needs to be faulty. Maybe both of them are faulty, but at least one of them needs to be faulty. Okay. So we have got this graph of measurements where the edge means that okay, these two contradict each other, and okay, so we want to like somehow like deduce which guys are contradictory, which guys are wrong. We know which guys contradict each other, but which guys were the wrong things. And usually like this like Occam-Reiser principle, usually the simplest, I mean the smallest or the simplest solution is the correct one. And because the probability of a measurement being wrong is very small, here I put 1 in 1,000 here, then actually, yeah, I put 1 in 1,000 here. Okay, then I put 1 in 1,000 here. Then we expect like 10 or roughly 10 errors. So in a sense, this is like a hard problem, like vertex cover problem. Yeah, if you look at this, I want to take vertices to explain or do contradictory things. But the point here is that during the algorithmic course or other courses, you learn that vertex cover problem is really uh, it's really a difficult one, and there's like NP hardness reaction. But here, the intuition is that the fact that we expect the solution to be small, that's only 10 guys are roughly 10 guys are small faulty, then this will make this problem easier. Yeah, this is like some sort of like the fact that there's 10. This 10 is sort of like a constraint that makes this problem much easier, or like this how many guys we expect to be in the solution. This can be thought as a hardness of the instance. Yeah, this is like the measure. Like if you expect 20 or 30, the problem becomes more and more hard. So, in a sense, this 10 is more important for the hardness of this problem rather than whether there's like 10,000 or like 20,000 or more, or like the solution, really the instance size here. Okay, let's understand the intuition more. So this was really the vertex cover problem. This is like the formal definition that, I mean, you know from Algorithmica probably, but let's just be on the same page. We have a graph and we want to select as small set of vertices as possible to cover all edges, so that after we delete these vertices, the red vertices here, this picture, we have got no edges left. Yeah, so this is the vertex cover problem. And because we work in this regime of like NP hard problems and like this sort of like complexity theory blah blah here, we want to think about decision problems. Yeah, so we don't want to optimize the size, we have got some threshold, and we want to find the vertex cover of size at most k, and this is like our task. We want to answer like yes or no, is there a vertex cover of size at most k. Okay, so this is the vertex problem that I introduced to you with some story on the previous slide. And yeah, so let us go slowly towards a good algorithm for vertex cover. So we have got this problem that we want the graph and find and a number, and we want to find the vertex cover system of k. So as during the Algorithmica course, we said okay, for NP hard problems, we don't expect polynomial time algorithms. There is nothing to be done with it. I mean, we think that they're all hard. So maybe here the only thing we can do is just to check all solutions. Yeah, there's like we can do like brute force exhaustive search here that just takes the graph and checks all sets of k vertices, or at most k vertices if the graph is smaller, and checks if this is a solution. Yeah, this is like a brute force algorithm. Like there are roughly n to the k things to check. I mean, n to the k choose. I mean, n choose k, but it's roughly n to the k is n is much larger than k. Yeah, so this is there, and there is like, I mean, the check whether all edges are covered. This is like times some linear in the graph size. Okay, so this is the algorithm, that's brute force. And the question is, can we do better? I mean, this is like n to the k. If you think about our numbers, it was 10,000, and we do it to the 10. This is 10 to the 40. This is like a very bad number. Yeah, if you think about 10 to the 40 operations on a computer, that's a no-go. I mean, that's like much more than your PC is going to cope there. Okay, yeah, so this is the problem, but let's try to do better. Yeah, so this is like this is like not good for 10, as we said. So, but we can do better here, and this is like our motivation example. Let's try to do better. And okay, so let's try to do a branching algorithm. So branching algorithm here is something like a recursive algorithm that intuitively will be very clear in a moment. So we want to find a vertex cover in the graph G of size at most k. Okay, and if there are no more edges, if this graph has no edges, then obviously there is an empty vertex cover, and this we're done. Okay, if there are some edges, but we don't case 0, so we ask a vertex cover of size 0, so we ask really a question, is empty set a vertex cover here? Then, well, there's no, so we have got answer no. Okay, and then what we do, this is like the trick. We take one edge from the graph. There is one edge from the graph. Okay, we take one edge, uv, and we say, hey, our vertex cover needs to take either u or take v, maybe both, but needs to take one of them to our solution. So let's try these two possibilities recursively. So let's try to take u to our vertex cover, and check if the remaining graph has got the solution of size k minus 1. Yeah, this is like the important property of the vertex cover problem we are using here, that if we decide to take one vertex to the solution, we remove it from the graph, and the rest needs to have a solution of size k minus 1. It is actually equivalent to the fact that the previous one has a solution of size k, including u. Yeah? So we check whether this guy has got solution of minus k, or this guy has got a solution of size k minus 1. Okay, and this branching, and this algorithm finds us a solution of size, a vertex cover of size most k, just because, I mean, by just in some sense checking all possibilities, but in a more smart way than we tried on the previous slide by just n to the k. It just takes an edge and thinks, okay, how can we cover it? Either we take this guy or we take this guy, maybe both, but that's not the matter. I mean, we need to take this guy or we need to take this guy, and we try both possibilities. Okay, let's try to analyze this algorithm that appears here. Well, let's import what's useful for all this type of branching algorithms here is to like think of like the recursion tree. I mean, how does the recursion tree of all the recursive calls revolves? So we have got like on top, we have got this call for graph g and k that we start from. And this guy gets to two calls with them g minus u and k minus 1 and g minus v k minus 1. Okay. Each of these calls either terminates because of some reasons or goes further into call with k minus 2, with two calls minus 2, and this one also k minus 2, k minus 2. Okay, so like what we have here is that in this branching tree, every node generates two recursive subcalls, but these recursive subcalls have got the value of the parameter, the value k, one smaller. Okay, so it's parameter one smaller. So we have got a tree which is binary. This recursive tree becomes binary. Every guy has got two children, and the height is k, at most k, yeah? Because I mean, after k steps down, k gets decreased to 0, and we end up here. We don't have any recursion further. So that's why this recursive tree has got roughly 2 to the k leaves, and we have got the running time of 2 to the k times size of the graph. I mean, there's like 2 to the k leaves and 2 to the k plus 1, I believe, nodes in this recursion. Okay, maybe there's some off by 1 error here, but it doesn't matter. So we have got running time like that, like announced here, that there's a recursion tree of size 2 to the k, and every recursive call, apart from calling children in the recursion, actually does some linear time work by just like, okay, making a copy of the graph without vertex u and making a copy of the graph without vertex v, and like checking if there's any edge or finding this actual edge left here. Yeah, so there's a linear work to be done at every step, and there's and the recursion tree has got size 2 to the k. Okay, and the point is that this running time is much more friendly if you think of like 10,000 vertices and k equal 10. Okay, because that's really 2 to the 10, which is like 1024 times 10,000, and this is like 10 million, which is like something bearable. So this is like much better than 10,000 to 10, and we didn't did that much work. Yeah, that was reasonably simple here what we did. Okay, yeah. So let's try to formalize what we really did. What's the really difference between 2 to the k and n to the k? What's the intuitive difference? And this is captured in the next few slides that are prepared here. Yeah. So recall that, I mean, this is the information like from, I don't know, Yao course or like some complexity theory course, that we think of like in a classical problem, we think that, okay, like we have got all 0, 1 finite strings are the possible inputs, and our language or our problem we're going to solve is just a subset of the strings that we should answer yes. Yes, so there's like the string comes and we should say yes if the answer to the problem is yes. And I mean, formally, if this is like a well-formed instance of our problem, blah blah blah, and the answer is yes. Yeah, so that's like a complexity theory point of view on the problem. Yep. And yeah, so there's like, yeah, so we think of like vertex cover, like there's some binary encoding of a graph, and we say yes to the guys that is a properly encoded instance, and there's a vertex cover size k. Okay, and now we change a bit the paradigm here. We have got what we had before. We have got in an instance, we have got this word that describes the graph or whatever is in the problem, but we also have got highlighted one integer. there's like one integer highlighted on the input, which we call the parameter. And this is like the important notion. This is like this 10 on the previous slide. So in some sense, think of a problem like this is think of a problem that the problem comes not only with like some setting like graph, find the vertex, cover, but also with like a finger pointed at one of the integers on the input, or one of the integers coming from the input, that actually like somehow like is the most important integer in this problem, and this is the which we want to refer to in the complexity. That's we can now use this integer in the complexity. It's not just the instance size, but also this integer, and we want to understand what's the role of this integer in the complexity of the problem. Okay, that's like the goal here. So in the vertex cover example, we want to understand what's the role of the size of the solution in the complexity of the vertex cover problem. Okay, so this integer, we use the fact that actually uh, this is like what we used was vertex cover parameterized by the solution size. So we took the graph, like somewhat encoded graph, but we said, hey, the size of the solution, the intended size of the solution, this is the like this is uh, our important number that we want to use in the running time bounds or like memory bounds. This is like important for the complexity part. But we can really, I mean, we ignore the encoding part. I mean, we're doing algorithms here, not complexity theory, so we ignore these encoding problems. They're not important for us. Okay, but we can think of different parameters. I mean, these parameters can be weird, and for some reasons, for some settings, they can be important. Like, for example, maximum degree of the graph may be sometimes an important parameter. Or something called tree. If you attended Algorithmica, you may have seen tree there. We are doing lectures on tree, but tree will also be very important in this lecture. So there's some structural graph theory notion called tree that can be used as a parameter and can be very important for the complexity of some problems. Okay, and the central question in this course is how, like, what's in different settings, how this number influences the complexity of a problem. Okay, so like we want to understand what are the possible running times of an algorithm where the important measure is not only the solution size but also the parameter. I mean, how this parameter governs the instance. Yeah, so in some sense, okay, if the parameter is small, can we do something smarter than doing brute force? Are there instances any simpler if the parameter becomes small? Okay, that's like our way how we want to think about this. Okay, so let's go to definitions of what we already did. So we aim at the following type of algorithm. This appears to be like, this was somewhat formalized in the early 90s, and this appears to be like the understanding where, I mean, it's like the same thing like the definition of the NP-hard problems in some sense, that you want to identify some class of running times, sometimes sacrificing some like practical matters, so that the boundary between like what's possible and what's not possible, I mean, where the algorithm exists and where the algorithm doesn't exist, is somehow like clear or easy to distinguish or like meaningful. So here it turns out, remember that we had this running time being 2 to the k times size of the graph. And here the important distinction, and we compared with n to the k. And here the important distinction was that this exponential part on k was like separate from something depending on the graph here. And here these two guys mix. Yeah, there's size of the graph to the power, and here there are actually two coefficients, one depending only on the parameter, and the second one depending only on the size of the graph. So it's like something depending on the parameter and something depending on the graph size or the instance size here. And here this was mixed, and this like separation that turned out to be the crucial property here, and this is highlighted in this definition. So we say that a good algorithm, a parameterized algorithm, think of this as like on this course the analog of polynomial time algorithm from Algorithmica course. Yeah, so this is like, okay, the parameterized algorithm, like the good guy, is the algorithm that takes the instance with this highlighted number and solves this problem, like correctly decides if it's in language. Like that means solves. That means solves. Yeah, in time, and in the running time, in the running time, we allow some polynomial depending on the instance size. So it can be n cube, it can be n to the 4, it can be linear, yeah, times any horrible function you would like of the parameter. So you can use something horrible, we use 2 to the k. That's not very horrible. You can use something more horrible, and that makes things sometimes not practical here. I mean, sometimes if you build here horrible enough function that even for like k equal 10 becomes like a no-go for practical applications, but like that's something that behaves well for all the reductions and like complexity theory stuff. So that's the distinction we make here. So this is like a good running time. Some horrible function of k times fixed polynomial in n, where this polynomial no longer depends on the parameter. So this is like n to the cube, not n to the k. Okay. So let us look at yeah. So what, because sometimes, okay, let me do one more thing here, because we won't be very much in this course, we won't be very much optimizing this polynomial time here, okay? And we won't, I mean, we will sometimes look at it, and it's sometimes very important, and there's sometimes papers really like there's some papers on a very good conferences that just like optimize this part, not breaking the f of k part of some old algorithm. But on this course, introductory course parameterized algorithms, won't be really looking at it. Sometimes we'll look like n to the O of 1, which means some fixed polynomial. Yeah, n to the O of 1 means like n cube, or n to the 4, n to the constant. Okay, so this is like shorthand notation. Like we will be sometimes abusing this like O of big O of notation here. This is one of the abuse we will make, that this means more or less this means polynomial in this course. Okay, so let's look at the examples. Like, do it seen 2 to the k times the number of edges. K factorial is a very good function. I mean, look that the plus is like smaller than product, so like doing a plus is also good for us. We can have more horrible functions like 2 to the k. We can have a towers. This is also a function of k only. This is when we stop to be practical for the sake of like being clean on the complexity theory side, but that's fine. What's wrong is being exponential in n. Wrong is being having k in the exponent even in a very weak fashion. So like even n to the log k, this is polynomial with the exponent growing with k. This is bad. This is not a parameterized algorithm. Okay, so this is like, I hope these examples make us clear. Okay, but this is like something like yeah. So this is like this is a parameterized algorithm, and this course will mostly focus on algorithms, not on parameterization. Not for algorithms, not like more complexity theory part, but so these are algorithms. But if you want to be formal, we say that the problem that means parameterized algorithms is fixed parameter tractable. Like this is the complexity class of algorithms admitting parameterized of problems admitting parameterized algorithms. Okay. And sometimes parameterized algorithm is called an FPT algorithm for this manner. And yeah, there's like we can formally say that FPT is this class of these languages for which there exists an FPT algorithm. Yeah, and this is like the main class we are going to study on this course. If you want to look and observe that polynomial time algorithms are FPT algorithms. There's just f of k equals 1, and so we ignore the 10 and just polynomial time algorithms are FPT algorithms, so we're studying a broader class of problems than just polynomial time solvable algorithms. But this thing, because we can do arbitrary bad thing on f of k, we are not contained in NP. Most of the problems we'll be studying here will be NP hard problem, NP complete problems within NP, but there is nothing to preventing us from solving like some horrible triple exponential problems here within this framework. Okay, so we are not constrained by this definition to NP hard problems, albeit the main focus in this theory is around the NP complete problems because they're like the most interesting for us. Okay, that's FPT. There's also another thing. So sometimes n to the k is not that bad. If you think of a problem, there's a classical example of the problem of like k coloring. Yeah, is a graph colorable with k colors? And here, if you have an n vertex graph, and you ask if the problem is k colorable, then you don't expect n to the k algorithm. Yeah, because already free coloring is NP hard, and that's the thing that you learned also at the algorithmic course. So free coloring is NP hard, which means that we don't expect even n to the k algorithm if we look at the parameter being how many colors you're going to use in your coloring of a graph. Okay, so n to the k is actually not the worst thing that can happen. The problem can actually be already hard for some fixed value of k, like k equal 3, and coloring is hard for k equal 3. Okay, so that's why we also make a class of problems where n to the k is actually doable. Yeah, n to the k is possible. So this is like something that's sometimes called slice-wise polynomial, because that means polynomial for every fixed k. Yeah, well, if somebody fixes k, I'm only interested in k equals 7, then the problem becomes polynomial. It can become polynomial in a very horrible fashion. It can be n to the 2 to the 7, so it can be very the dependency on this k in the exponent can be very horrible, but it is polynomial for a fixed k. And that's something called XP algorithm. This is like slice-wise polynomial usually. I mean, XP, somebody wrote XP, but the usual name is slice-wise polynomial. Like every slice of fixed k is a polynomial time problem, polynomial some sort of problem. Yeah, so this is it. So the good examples, I mean, the good and bad examples are like all the FPT things are also, yeah, because we allow more here in the running time bound. So all FPT is XP, but also we allow n to the k, n to the log k, n to the horrible function of k, but we don't allow n in the exponent. Yeah, we don't allow n in the exponent. Okay, and we have got this class of XP of these problems that admit an XP algorithm, and we just observed that okay, P was in FPT and FPT is in XP because the FPT we make one extra restriction that this exponent of n cannot depend on k. Okay, so that's the complexity definitions that we are going to use here. And this is I think what we're doing. There's a small discussion here about why do we use decision problems that simplify our thing, but usually when we'll be doing algorithm design and not caring much about the complexity side, we'll be thinking in terms of like how to optimize the number of vertices here, or how to like we'll be thinking sometimes into like optimization function, but like formally we are solving decision problems, and we are doing like we're doing really like here more theoretical analysis, but sometimes like some applications with type of form it. Okay, and in most of the problems we're solving, like actually giving the solution or like optimizing the solution will be quite straightforward. Sometimes when we go to more algebraic algorithms, sometimes like extracting the solution will be a challenge, but we'll discuss it when it happens. Okay, good. So we spent the first 40 minutes on like some examples and discussion what we were doing here. So let's go to some meat and like depart from this complexity blah blah that we were doing here, and let's go for like some really branching. Yeah, so let's go for branching. And what we did here, yeah, remember this branching tree we had? We had like some GK, and we had like at every step we uh, we branched into like two directions. Yeah, go take one endpoint of an edge and one take another endpoint of an edge, and the depth of the recursion was k. Okay, and this gives us this 2 to the k times some polynomial spent, like that was linear actually, but times some like polynomial spent at every vertex, at every node of the recursion, yeah, to analyze what we are really doing at this point. Okay, so that was the the thing. But the observation is that if we want to aim at like some horrible function of k times polynomial in a running time, we don't really, we have got some we have got some like we've got some like freedom here. Yeah, this 2 can actually be any function of k, and this height can be any function of k. Yeah, it's perfectly fine to have got like to do the k, to have got, I don't know, say let's change color and red, let's color, it's perfectly fine to have like, I don't know, 2 to the k options to choose from, and the depth of the recursion being k square. Okay, if the depth of the recursion is k square, and if we have got 2 to the k options at every step, then this tree will have got 2 to the k square, which is 2 to the k cube leaves of the recursion, and it would still be something like 2 to the k cube times polynomial in n running time bound for the, and this will be still FPT algorithm. Yeah, so the general idea is to have got some branching where we make at some moment some local decision, usually a local decision, like okay, we can do this one in this f of k options, and the depth of the recursion is bounded by some other function of k. Yeah, so we actually have got some limit. I mean, we made some progress, some really measurable progress at every step. We'll see more examples in a minute. Okay, so in the vertex cover, there was like 2 options at every step, and the depth of the recursion was k. Okay, that was a bit abstract. Let's go for a simple example, and there will be more and more examples on the lecture and the tutorials. So let's go for feedback vertex problem. Feedback vertex problem is really a problem, and this will be important for your quiz. So the definition of this problem, feedback vertex problem is really a problem of like, I have got some graph G, and this can be directed or undirected. These are two different problems for direct and undirected graphs. And I want to enter some integer k, and I want to find some subset of the vertices so that has got no cycles. Yes, this is written down here, but it's written for tournaments. But in general setting, the feedback vertex set problem asks you to delete at most k vertices to make the graph acyclic. And now, if the graph is directed, that means no directed cycles. If the graph is undirected, then not cycles means a forest. So this problem behaves differently in directed graphs and undirected graphs because forests are quite simple problems graphs, and acyclic directed graphs are more complicated than forests. So these problems behave differently in these two regimes, but there's just a common name for these things. And here, on this example, we restrict to tournaments. Tournament is really tournament is just like between every guys there's an edge in one direction. Yeah, tournament because it's like a playoffs, like there's some teams and node is a team and every two teams play the game and there's like arrow in the direction of who won the game. Okay, and this is the tournament. Yeah, so every two nodes were compared by, and there's an arrow in your direction. Yeah, so now we want to delete k vertices from a tournament to get the graph, to make the graph acyclic. Okay, make the tournament acyclic. And feedback vertex said, like, the problem was that in the vertex cover we're deleting vertices to kill edges, and here we are deleting vertices to kill cycles. The nice things about vertex cover was that we are deleting vertices to make delete edges, and every edge had two cycles, had two endpoints. Okay, every edge had two endpoints, so we actually could look at this edge that we want to kill and branch, delete this endpoint or delete the other endpoint. Okay, so we want to delete one endpoint and the other endpoint. And now think of that like our obstacle, or our like thing that we want to kill is a cycle. And the cycle can be very, very, very long. Okay, and there can be many vertices. So like the branching factor, like how many options do we have at one step, may be unbounded as a function of k. Okay, so there can be a long cycle, and we cannot branch into all options which vertex on the cycle to kill. Okay, luckily in this problem we're looking at tournaments, and the tournaments are somewhat simpler because there are edges everywhere. Yeah, there are edges everywhere. So in tournaments, this is an example here what to kill. In tournaments we may have long cycles, but if we have long cycles we also have short cycles. So in a tournament, we have got the observation, really, like lemma is like a very strong word, that if the tournament is not acyclic, like a cyclic tournament is just like a total order, yeah, all the arrows go in one direction. But if the tournament has a cycle, then there is actually a triangle, a cycle on three vertices. Why? Let's look at a cycle, and like, well, these two guys on the cycle, they need to be connected by an edge, yeah, in one of the directions. If this direction is like that, then there's a shorter cycle here. If this direct edge is like that, then there's a shorter cycle here. So like every cycle that's not a triangle, that's not a free cycle, can be shortened to a shorter one, and then in the end we get a triangle. Okay, so the shortest cycle in a tournament is a triangle, unless this tournament is a cyclic. Okay? So we have got this lemma. So what we can do exactly the same we did before for vertex cover. Okay, if the tournament, but we just use this one tiny observation. If the tournament is not acyclic, so if the tournament that still has a cycle, then, so the empty set is not a solution, then there's actually a free cycle, and in this free cycle we have three options which guys to choose. And this is the argument here, yeah? If we run out of budget, we say no. If there's actually a, if we are already acyclic, then we say yes. If there are no triangles, we are already acyclic, we say yes. Otherwise, we take one triangle and kill one of these three vertices and recurse. And again, we have got now a branching factor. Like in every step, we have got three children. Every recursive call has got three children with parameter k minus 1. And the depth of the recursion is k. And the depth of the recursion is k, so we have got 3 to the k leaves of this recursion, and this gives us this type of rank time bound. Okay, this was not very more complicated than the vertex cover example. Just we needed to look slightly more closely on what we're actually killing and what are the limited options at every step. Yeah. So yeah, that's the thing. Good. So that's what I prepared slides for. So we are in the middle of the lecture. These were the simple examples. I put thanks to the slides, and because slides were not my only by me, but it's like a Frankenstein. Now I'm going to put, like on Moodle, there's a link to OAup. I'm going also to put this link in the chat. Okay, so let's go to this OAup there. I'm also going with this OAup. We can also look at what I'm sharing here, because I think I have got this OAup opened here. Yep. Yeah, so you can look here, or you can look at the OAup directly if you prefer. And I'm going now to go for some things on the whiteboard to present to you and to like actually there. I think all of you can actually draw at this OAup. Oh, there's actually some chat. No, there's not. No, that's so I see that you're joining OAup, so I'll give you a minute. This is a good moment to ask any question if you have. Ha, there's a lot of people joining. I will slowly start to write, but I mean, I will try to slow down for a moment so that you can join the OAup. I want to show you 2 or 3 examples, depending on the time, for more complicated branching algorithms up there. Okay, so this is like this whiteboard here. So the first problem, I want now to depart from graphs. So as you will see, like 95% of the course will be about graph problems. So now I'm going to make not a graph problem. Okay, it's my not graph problem. Namely, I want to look at the problem which is called closest string. So the closest string problem, there is some alphabet sigma. There's some alphabet sigma, and we have got some integer n and some integer d. Okay, these are integers. And we have got a number of strings. So we have got some strings s1 up to sk, or actually I will call them just to call it t, just not to confuse with the parameter t. And these strings are all strings, so they're strings of length n. Yeah. So think of them as you have got like a string s1, a string s2, and up to a string st. Okay, so we've got like t strings, and they're all of the same length n. Okay, good. So this is the input to the problem. So this is like the input. And the output, what we are going to look for, we're going to look for something green, and the output will be, we want to find some s star, which is also a string of the same length. Okay, so we want to find some extra s star of the same length, and we want this string to be, I want the string to be close to all the other strings. So we want for every I from 1 to t, we want the distance, the Hamming distance between s star and si to be at most d. Yeah. Oh, there's somebody kicked out from Zoom. Sorry. Okay, so I'm trying to experiment with Zoom. So I needed to put all of you inside. I thought I configured the Zoom so that all of the you that come with the uw.edu.ppl, like uwu.edu.pl address, go in immediately without being admitted. Yeah. So I will try to check my details, but I made this Zoom conference using the university account, and I think all of you admit, if you come from the uwu.edu.pl account, you will be admitted. We will admit it without me admitting you by hand. But I'm not sure. I will check the settings afterwards if I did it correctly. And the guys from Jagiellonian University that are with us, I'm sorry, I need to put your manually inside because you don't have account here. Okay, good. So this is the problem. Yeah. So let me just hope that it's clear. We have got a number of strings of the same length, and we want to find an extra string of the same length that's like close to all of them. And there is some number d, which is there's some number d which governs what's the allowed distance. Okay, what's the allowed distance here? And yeah, So I want now to present you an algorithm to solve this problem, and this algorithm will be using d as the parameter. So this is our parameter.
How do we define the distance between two strings?
This is Hamming distance. Like how many letters are different. So this is like
Okay.
yeah, this is like a Hamming distance. You just put them one by one, side by side, and you compare how many letters are different. Sorry, this is like Hamming distance. Let me just put. Yeah, this is like the natural one. You just compare position by position how many things are different. Okay, good. So now I know that this our app has got problem. Oh, let me move down, and let me try to now go back to Blackpen and try to make a solution. Okay, so I want to make a branching algorithm. Okay, so this branching algorithm, the intuition is that I want let's try to make a candidate. So let's start with like a candidate initially. What's that? So initially, let's take my candidate to be one of the strings. I mean, one of the strings is a decent candidate. I mean, it's at least close to one of them. Okay, it's a good candidate. Okay, and maybe this is okay. Yeah, maybe this one is okay. Yeah, so this is initially. So maybe let's check like if the distance, like if for every I, the distance between S and Si is at most D, then it's okay. Then we are done. Yeah, then we are done. We return the solution, like return the solution, return yes, then yes. Okay, let's say yes. I mean, probably I should say yes to be consistent with the slides. Then say yes. Okay, so if we're fine, then yes. But what's wrong? Yeah, so else we have got some Si, yeah, where does I be? So we have got some Si, we have got some I is larger than D. Yeah, there's exist some I. So we have some I. We have got some strings that's too far away. Okay, but how far away this string can be? Okay, the point is that this string cannot be very far. Yeah, what I want to say is that I want to say here that if this distance, like if this distance between S and Si is larger than 2D, then we say no. Yeah, because because yeah, if we started with like the string being one of the strings, okay, we started with the string being one of the strings, and if there's another string within distance 2D from them, more than 2D, then we don't have an answer. Yeah, because this Hamming distance is really a metric on the like space of strings. Okay, it's a metric on the space of strings. So if you have got two so if you have got so if you want to have got this answer as star, which is up there, and is within distance to one of them, within distance d to other, d with one of them and d to the other, then between these two guys, the distance can be at most to d. Yeah, this is like, okay, this one differs on d positions with one guy, on d positions with the other guy, so this guys needs to differ on 2d positions at most between each other. Okay, so this is no, but okay, but else, what we can do else? Well, else, in a sense, we need to get closer. We need to make a step towards this guy that's like too far away from each other. I mean, our solution needs to agree with this Si on one of the positions. Okay, so we want in a sense we want to flip our current solution S on one of the positions when they differ. Yeah, so like return or so like if for every j from 1 to n such that Si of j differs from S of j. Yeah, this is like yeah, so for every of that, let me move below. Okay, for everything like that, just recurse if like this recursion. Yeah, so let's like this call. Yeah, and I want to now in S flip the position j to Si of j. Yeah, with this one call this one's recall. Okay, I will put up there, then yes. Let me just finish up there and return no. And this is like call with some s up there. Okay, so now I will say I will put here also some allowed budget p, and I will put here p minus 1, and I will put here, let me just put a color, I'm just putting something, and I will just explain. I will put here d plus p. Okay, and the initial call at the very top, I'm running out of space, and the initial call means that I'm calling, call s1 and t. Okay, this is the initial call. Yeah, so now let me try to explain this algorithm, what I presented here, just like the realization of the idea here. What we did here, can I zoom out it a bit? Yes, I can. No. Okay, this is like, okay, I have got two, sorry, I'm just learning how to use it on tablet. I think this, oh, that's better, good. So now what I want to say here is that, good, sorry, I will slowly learn how to use it, okay? So what I want to have here is that, okay, what I'm doing here is initially I'm calling like, okay, I started from S1 and my solution is within distance D from S1. Okay, that's like the initial intuition. Like I started from S1 and I'm looking for a solution within distance D. Okay, so this is like what I'm trying to do. Okay, here. Yep. And okay, so and the S is like my current guess for the solution. Okay, and if if this is really a solution, then okay, I found the solution, I'm happy. Otherwise, there's actually like, okay, it's actually a guy within distance more than D, but if I'm looking for a solution, like I've got S, and I've got within distance P from it, I'm looking for a solution within distance P, okay? And there's another guy, Si, that wants to be the solution within distance, that wants the solution to be within distance D from each, okay? That wants the solution to be within distance D, okay? So in order to find the solution within distance P from S, then actually better this distance from S to Si be at most D plus P, otherwise we have got no chances of finding a solution, okay? Yeah, because we want to find a solution within distance P from the current guess S, okay? This is like the idea of the there. Yeah, so this is why we changed here, like, okay, within if the distance is too large, then say no. Otherwise, okay, this guy is within distance more than P, one more than D from us, okay, but it's within distance at most D plus P, so we want to flip one of the letters to be closer to Si, yeah, because one of the letters of our solution needs to be us in Si, not us in our string, okay. So that's so we yep. So yeah, so we need to flip it, and we just guess because we have got D plus P options, at most D plus P, which is at most 2D options, which one to flip, and we recurse in every options. Yeah, so we do the recursion here, flipping one of the letters to the one that's actually in Si, not in S. So we change one letter at the time, and recursively, okay, so what we do here, we actually take green color, like go to all the neighbors that are in the direction of Si, like go to all the guys that come by flip of one letter that are closer to Si, and from these guys, try to find something within radius P minus 1. Okay, within the radius P minus 1, within P minus 1 steps. So that in the recursive call, where we actually made the correct guess, that we flipped the correct letter towards the SI, then actually we made some progress, and this recursive call will make the correct, will actually find our solution. Yeah, and okay, yeah. So this is like in a sense what I told you. Let me try to make it again. This is actually like a proof of correctness of this algorithm. Let's try to go over it again in a more formal fashion to see how this proof of correctness should go. So what we say here is that the recursive call for SP looks for a solution within distance P from S. Yeah, so is there a solution? Is there a solution within distance? Yeah, within distance at most p from S. Yeah, this is really what this recursive call does, and we start from like looking at distance d from one of the strings we start from. Right? That's really our question. Okay, and we start with checking if S is a solution, like if the center of this like p ball is a solution. If it is, then we report we are happy. Otherwise, we observe that, okay, every other thing needs to be within distance d plus p, otherwise we have got no chances of finding a solution, okay? And if we have got a guy that's like this too far away, but still within distance d plus p, then the solution needs to have got one letter, not as in our candidate S, but as in Si, okay? So we flip this letter, and like the distance between Si and the solution, if we guessed the correct letter, the distance between Si and our solution we are looking, between S and our solution we are looking for, will decrease by 1, because we change one letter as it is in the solution we are looking for. Okay, so that's why we can now focus on the balls of radius p minus 1, and in this manner make a progress. So now in this, if you look at the analysis of the running time, now every guy will have got at most 2D children in the recursion tree. The depth is d, at most d, because we decreased p by 1 at each step. So this is really 2d to the d times polynomial in n times polynomial in the input size running time. Okay, so this is really like 2d to d. So this is FPT parameterized by d running time. Yeah, so this is like the running time we have here. Okay, and yeah, so that's like the that's what that's the algorithm here. The important part here is that there's like two important things here, or like two interesting aspects of this was. First, we have got quite a lot of options. Yeah, it's not that we just take a vertex or not, or take one of the three vertices. We really took quite a few options here, like at most 2D options, what to change. So we use this power that we actually can have like many options. I mean, it still needs to be a function of D, but many options. And like somewhat the measure of the progress, like within which distance we are looking for a solution, that was like somewhat like a non-trivial measure of progress. You know, it was not just decreasing budget for the solution. It was like, okay, how far we are from the solution. Okay, so that was one example I wanted to show you. And in the remaining part, I see that I won't go to the most complicated example, but that's not very worrying. But in the
May I have one more question?
Yes.
What happens? I don't see why it cannot happen here. What happens if, for example, first I have S1 and later I found another string which like, you know, I have to change a letter. I changed this letter, but later I found another word and I changed the same letter. Is it okay here, or?
I mean, it's okay. I mean, it's okay, but I understand the confusion. So the point is that what we really want from the branching algorithm, we want that if it finds a solution, then actually this is really a solution, and in this part this is obvious. Yeah, that actually, hey, this algorithm will actually like, if it finds a solution, says yes, then it really finds a solution because it's verified by hand that this is really a solution. The other thing we want to say that if there is some solution to find, it will actually find some solution. Yes, that actually we want to lose the solution on the way there. And the way how we prove it here is that, hey, maybe in some branches it will actually change a letter back and there and do some stupid things, but there will be like some path of computation. You can think of it as like, I don't know, non-deterministic or something like that, but there's a path of computation where it will make the correct guesses. So you think that there's actually somebody advising the algorithm on the back. And actually at every step, when it tries to do this branching here, it actually says, hey, change letter 17, okay? Then actually there's a computation path that leads to the solution, because at every step you get one step closer to the solution. As the distance between S and the solution you're looking at, like fix one solution, S star, the distance gets one closer at every step. So the algorithm may in some branches go back and there, and we don't need to keep track of it. I mean, there's this P that like somehow limits the branching, but there's one path of computation, like one path in this branching tree when we make all the time the correct decisions. And in this path, we want, in particular, we want to change the letter back and there, and we'll actually find the solution there in this branch. Yeah, so we need only to prove that the algorithm will find a solution in one of the branch. We don't care if it does something nonsense in the other branches, as long as it doesn't spend too much time there.
Okay, and what we denote with P?
P is the distance we are looking at. So we started with like call P equal D. We started with P equal D. And at every step, like the definition, like if you want to make a formal proof, you write that call SP checks if there is a solution within distance P from S. And like at every step, which decrease this P by 1.
Okay.
Okay, thanks. Good. Any more questions? Okay, so I want to spend the remaining 24 minutes of the lecture on actually trying to like show you how to try to optimize or squeeze as much as possible from some branching algorithm. So let's go back to the vertex cover. So we go back to the vertex cover. I'm going down, and we go back to the vertex cover, and let me write down the algorithm. Okay, and let's try to optimize this algorithm. So let's try to go back, and we go back to vertex cover. Yeah, and I want to optimize this algorithm. So let's try to make a few things. We did the following. We did the first thing I want to say is that, okay, we did this edge. We take an edge and delete one of the endpoints. But if you want, if you think about it for a moment longer, then actually, if you can think of the following branching. Look at V. Look at vertex V. If it's in the solution, you just delete V and decrease K by 1. Okay. But if it's not in the solution, then you not only need to include U, but you need to include all the neighbors of V, because all this address needs to be covered. Okay, so you have got some better. If you try to like optimize this branching algorithm, you have got a better option, like either take V or take all these neighbors, and these are much more of them, so K gets decreased by much more. Okay, and this looks like some progress, so we'll get a faster algorithm by this. Let's try to write this algorithm here. Okay, so let's try this vertex cover algorithm, vertex cover of GK. Yep, and which vertex makes sense? The most? I mean, let's take the vertex of the highest degree, because then this gain of taking the neighbors will be the largest. So let's take V. I will leave some space here. I mean, we have got this stupid things like if G is edgeless, if G is smaller than 0, then no. If G is edgeless, then yes. We have got the stupid things. And let's write here at the bottom, I will just erase this guy and write it. I want to leave some space for some extra preprocessing here. So I want to say that let's take V to be the guy of highest degree. Max degree vertex, and like return a vertex cover of we either delete V and decrease K minus 1, or we take its neighborhood. Yep. So we take its neighborhood. So what we do here is that we either delete the vertex or its entire neighborhood. Okay. And now, well, what we can do here, well, how big this neighborhood is. Yeah, well, it can be a vertex of degree 1. Yeah, okay. It cannot be a vertex of degree 0, because if there are no edges, then we return area. But it can be a vertex of degree 1. But if the maximum degree of a graph is 1, then vertex cover is not particularly challenging. Yeah, it's like a magic. Yes, just count the edges. Also, if the maximum degree of a graph is 2, then the graph is paths and cycles. Vertex cover is also not particularly challenging in this graph. Vertex cover starts to be actually interesting when the maximum degree is 3, and actually you can prove that it's actually NP hard in the graphs of maximum degree 3, so we better not try to do something very smart there. Okay, but what we can do here, we can add here is that what we can add is that if the maximum degree is at most 2, then like solve like, I mean, I won't write here. I'm pretty sure everybody here is able to solve vertex cover with graphs of maximum degree 2. Okay, so what we actually can say, okay, if the graph has got maximum degree 2, then just do some simple things to solve it. Otherwise, let's branch out the maximum degree vertex and see what happens. Okay, so let's look at the analysis here. So now we have got vertex, we have got G and K, and we choose a vertex, and in one option, K decreased by 1, but in another option, K decreased by the size of the K decreased by the size of the neighborhood. which is at least decreased by at least 3. Okay, this is decreased by at least 3 because this vertex was of degree at least 3. Okay, so now we have got like a branching tree. This branching tree now stops to be like a maybe full binary tree of depth k and 2 children each, but like in one direction we decrease k by 1, but in another direction we decrease k by 3. So if we go like rightmost path here, if we do like rightmost path here, then actually it cannot be like k steps, it's much shallower. And I mean, at least the guys that attended discrete mathematics with Professor Malinowski know how to estimate number of leaves in such branching tree. Just write a recursion that t of k is like t of k minus 1 plus t of k minus 3, and you solve this recursion, and there's like a known way. I mean, I'm going to go into this. Let me go down. But what you just, I mean, this is something that was done at least for some of your discrete maths course. I mean, you think, okay, this is like, okay, just do it like that. I'm going to the site here. It's almost me. I'm going to the site. Yeah, well, how you solve these things? Well, you do. Well, you think of the following. You write that this is actually some x to the k, that t of k is some x to the k, and by reducing here, you actually get an equation that x equals x to the minus 1 plus x to the minus 3. You solve this equation by your favorite numerical solver, and you get, and I put notes here, that actually I have notes. Let me just open them. You have, I think you get here that this is 1.4656 roughly. Okay, this is roughly like that. Yeah. So actually what we did here is that we got an algorithm with running time 1.4656 to the k times size of number of edges by just doing this, like changing branching into, okay, let's branch on the maximum degree vertex, and if this maximum degree is most 2, then do something naively. Okay, so we replace 2 to the k by almost root 2 to the k half. I mean, okay, this is slightly more than root of 2, but we actually, with this small trick, we optimized our branching by some small by the base of the concept, and you can mine it further. I mean, there are further options like what to do here or what to reduce here, and yeah. So I want to show you how to try to optimize it further during the last 15 minutes, but I want to change the measure. I mean, we use the fact now, okay, we were doing parameterized algorithms here. We use the parameter k, the size of the solution, but I want to use the parameter n. So I want to think, okay, I want to change the paradigm, and this is such a paradigm. Okay, in this course we will be doing parameterized algorithms, and we'll be looking at different parameters. Formally speaking, number of vertices of the graph is also a wide parameter, and you can use it. I'm now using number of vertices to show you a technique how to like analyze it, and because it's better visible on the number of vertices, it's not that easy to do it with like the solution size. So let's try to analyze it, like what's the best time for making vertex cover when you want an exponential algorithm. You don't care about k, you want c to the n. Yeah, so you want really c to the n algorithm for vertex cover, and like the brute force is to the n, like the baseline. I mean, just check all the subsets. This is to the n algorithm. Okay, so let's try to go for the vertex cover, and well, let's analyze this algorithm in terms of n. So now we want to analyze this algorithm in terms of n. And now let me make, I don't know, green color here. Well, and now k decreases, but I mean, what's the n here? So now we have got n vertices here. I need to change to pen. There are n vertices here, okay? And here we lost 1 vertex, and here we lost at least 4 vertices, okay? Here we lost at most 4 vertices, at least 4 vertices, because we lost v and the 3 neighbors of v. Yeah, we are now measuring how many vertices got deleted from the graph. So now this one becomes here k minus 4, and we solve it the same as well. And I have got put note that now this is like something like 0 here to the n. So 1.3803 to the n. Okay, so this is this. I want also now to like optimize it further, and I won't do anything much more. Okay, and I want to say, I want to add, so I want to take a red, oh, actually a magenta. a pink color, and I want to add here a reduction while there exists u of degree at most 2 reduce, at most 1 reduce. So all of you can actually find a good way of actually like reducing vertices of degree 0 and 1. Yeah, if you have got a vertex of degree 0, if you have got a vertex of degree 0, then you can just delete it. It doesn't play in the vertex cover game. It's completely irrelevant for the problem. If you get u with one neighbor u prime that may have got more vertices, you need to cover this edge, but you can greedily take the other endpoint. Yeah, you can take the neighbor of u. There's no branching here. If you have got vertex degree 1, you can greedily take the neighbor of this guy to your solution. And that's it, okay? So you can add here a reduction rule that just gets rid of vertices of degree 0 and 1. This is like simple. And now I want to say that with this augmentation, actually, this algorithm is better than this one. Okay, how do I do it? I want to say that this algorithm is better than this one, but how do I do it? I mean, formally speaking, here I didn't have any gain here. I mean, still I can branch of the vertex of degree 3. I can branch on vertex of degree 3 and have got this n-1 and n-4 here. Okay, but the intuition is as follows. If I branch on vertex of degree 3, then all the neighbors needs also to be of degree 3 or 2, okay? Because I took the highest degree vertex. So the degree of these neighbors decreases. It decreases from 3 to 2 or from 2 to 1, and then this 1 gets, I mean, I'm talking about this branch, yeah? I'm deleting V, and these neighbors, they degree decrease by 1. And they degree, if I was branching at the vertex of degree 3, then this degree is decreased from 3 to 2 or from 2 to 1. And the decrease from 2 to 1 is a very good decrease because then this guy of degree 1 will get reduced. Yeah, it gets reduced here. So we'll actually lose one extra vertex in the consecutive step. So we want to think, okay, decreasing from 2 to 1 is great, but from 3 to 2, I mean, this is not, I mean, okay, this is something that's okay, it will maybe decrease to 1 in the future, but so far there's no gain so far. I mean, we didn't reduce here vertices of degree 2. Okay, so what we can do. So the idea is to actually somehow like measure the instance in a different fashion than the number of vertices to somehow say that something progressed already in the direction we wanted to progress. So let's define it. I'm just going now down, and in pink color, I want to say the following. I want to define the measure. I want to define the measure me, okay? And this measure on a vertex is the following, okay? I put 1 if the degree is large. I mean, these are the difficult vertices. And I put half on the degree being 2, and I put 0 if the degree is smaller. Okay, this is the intuition that a vertex, when it's, as long as it is degree 3, then it's difficult vertex. Then it may get decreased to degree 2, which is still not reducible. It's still present in this graph. It's somehow important for us, but somewhat like it's one step away from going to degree 1, and it's not something we'll branch on. Okay, and degree 1 gets reduced in a moment, so it is weight 0. Okay, and of course, like, and we think of like the vertex G, the measure of the graph is like the sum over the vertices measure of the vertex. Yeah, so we measure the, like, we say, okay, this are like the vertex of degree 2 is only a half in our measure. Okay, and now let's try to analyze our algorithm as like C to the constant, C to the measure, not C to the n, not C to the number of vertices, but C to the measure. Okay, and yeah. Okay, so let's try to do it, and let's try to analyze our branches. So of course, this measure is smaller than the number of vertices. I mean, not larger than the number of vertices, because we know vertex has got weight more than 1. But let's try to analyze our branch, how our branching works. Okay, so let's try to analyze our branch. So we have got the following. Yeah, so we have got like we branch on a vertex V. Okay, and there are like there are 2 cases depending on, remember that previously our difficult problem was when the degree was 3, okay, because then only 4 vertices get deleted in the other option. So let's first do case 1. The degree of the vertex V is 3, okay, so we branch over the degree vertex. Okay, so this vertex, so there's the branch when this vertex gets deleted, and there's the branch when its neighborhood gets deleted. Okay, So what's the decrease in the potential here? It gets 3 neighbors, okay? But the point is that, okay, I deleted this vertex, so I decreased the potential by 1 for this vertex, okay? But these guys, they got the degree decreased by 1, okay? And they cannot have degree more than 3, okay? They cannot have degree more than 3 because we took the maximum degree vertex. So these guys have got either degree 3 or degree 2, maybe this guy has got degree 3. But in both cases, by deleting V, we decreased their value by half, they weight by half, or they measure by half, okay? So what they all lose half on this measure, okay? So in this branch here, we lost 2.5, okay? We lost 2.5 here, okay, by deleting V. And if we delete the neighborhood, okay, we delete neighborhood, it may actually happen that this guy has got weight 1, but this guy has got weight half because they have got degree half, so we may also lose 2.5 here. I mean, this case can be of degree 3, and then they have got weight 1 and we lose more, but we lose at least 2.5 because this guy has got weight 1 and the neighbors have weight at least half, okay? So the recursion here in this option becomes now, the recursion here now becomes T of K is like 2 T of K minus 2.5, and this is better than the previous one. Remember that the previous one was like K minus 1 or K minus 4, and here in some sense we balanced out. There are 2 losses of 2.5. Okay, this gives a better recursion. This is this intuition that if you have got K minus something and K minus some other thing, and you trade off these numbers, like one gets smaller, one gets higher, then the closer there are, the better recursion, the smaller base of the exponent there is. Okay, so this is like better than the previous one. We already made the progress. But let's look at the other case. I mean, this is like case degree 3. Let's look at the other case. I'm moving to the side and looking at the other case and taking like one extra color. So case 2, I will learn once. So in case 2, the degree of vertex is larger than 4. Then, well, this vertex has a degree 4. Okay, but these neighbors may also have got degree 4. So this guy lose 1. Okay, but maybe these guys have got degree 4 as well, and maybe I don't lose any weight. So we have got loss of 1 in the case when we delete G minus, when we delete only vertex V. If we delete neighborhood, okay, well, there are at least 4 neighbors here, and they may have got weight 1 or weight half. They may be of degree 1. Okay, they may be of degree 2, and they may have got weight half. Okay, but if they have got weight half here, then here there's like they also lose weight here. Yeah, so let's make A to be the number of degree 2 neighbors, the degree neighbors. So here we lose a half, and here we lose minus 5 minus a half. Okay, yeah, so what we do here is that here we lose 1 vertex, and every neighbor of degree 2 gets reduced to degree 1 and gets reduced, so we get an extra half from it. But here all the neighbors gets deleted, but the neighbors of degree 2 have weight only half, so our loss in weight is 5 minus a half. Yeah, because we lose 5 vertices, but a of them have got weight half. Okay, and this again, this balancing. I mean, the worst case if a is equal 0, yeah, because then this number is the smallest and this number is the largest. So like this is the most imbalanced, taking the same sum. So this is like the worst case when there's like t to the this is like really t of k is t of k minus 1 plus t of k minus 5, which is again better than the previous one. There was k minus 4 before. So we made some progress, yeah? In both cases, we have got better this branching recursion. This is sometimes called branching factor, branching vector. These things. And there we have got this better branching vectors than we used to. So we have got some progress. And now I again took notes of this one. And let me find my notes. And this is actually 1.3246 to the n. Okay, so this is actually something like, this is actually like, and this, yeah. So this is, yeah, so this moment when I want to stop with this type of analysis, this is something I want to highlight you. I don't think we'll do this type of analysis anymore in this course, but there's quite a complicated technology of like analyzing this type of branchings when you delete some vertices and like you put weights to different things, and you actually at some moment end up actually having like 5 different variables for like weights of different objects, writing the recursion, then using some numerical software to find you the best weights or something like that. And this method is actually called something called measure and conquer. Yeah, it's something called measure and conquer. I mean, somebody called it measure and conquer at some moment. I will write it here, measure. I think this is a pun about this divide and conquer, which is in every algorithm textbook. And then somebody said, okay, but we actually sometimes win by having the better measures of what we are actually having in the instance. And then somebody called it measure and conquer. There is a textbook of Fomin and Crutch wrote a decade ago that have got a lot of this type of examples. And this is like up there. So there's quite an industry. It was very live like a decade ago, and people invented that for many problems you can actually mine a lot of options up there, but somehow like the important things were already invented then and then somehow died out in the last decade, I would say, or not much happened there. But yeah, you have got like this type of measuring, you can get quite a better and better base of the exponent. We'll see this type of reasonings. Also, there's a lecture on LP branching somewhere in the middle of the course. We'll be using a very different measure, but also this reminiscent of sometimes like measuring and understanding what's difficult and like mining branching cases will be present there on that course as well, on that lecture as well. So this is the intuition. Yeah, so we use the n sine number of vertices here, but you can try different ones. Yep, so I think I'm going to end here with the thing, with the lecture. With the things, just to remind you that there's a quiz that, yeah, I mean, the quiz is supposed to be simple, but you need to have a perfect score to pass it. I hope I will try to configure it soon. I mean, I hope I configure it correctly. We'll see how it goes. And you have time until next lecture, and I will take any questions if you have.
I have not a question, but a remark. Like the current board is temporary, so when we all leave it, it will also disappear. So if you want to save it, we need to, I don't know, export it to PDF something and
I'm trying. Okay.
like, do it and put it into Moodle or something.
Okay. I just put. Okay. I think I just got the PDF from the. Yeah, I have the PDF, so I put in the PDF into the Moodle. Okay.
Cool.
Thanks. Any more questions? I'm just checking on the course if there's like.
I just wanted to make sure there are no tutorials today.
There's no tutorial today. The next tutorial is next week, and Wojtek will announce the details. And I just see that in the Moodle in a minute, the tutorial will be, the PDF for the problems will appear in a moment.
Okay, and these groups of 4 people, how do I know which one of them I'm
It's
in?
also on the Moodle.
Oh,
There is
okay,
like
okay.
group, I mean, it will appear in a minute. I think it's scheduled to appear in a minute on Moodle.
Okay.
There's a group composition on Moodle, and yeah. Good. Please try to contact. I mean, if you have problems contacting other people, let us know. I think I made. I mean, there are emails or index numbers in the emails, so I hope you will find.
Okay. Thanks. I have also another question. I'm not sure if this was mentioned. Is there some website where you could like test your code for parameterized algorithms? Like, you know what I mean, like these sites where you upload your code and.
I don't think so. I mean, we had a few programming challenges. There's something called PACE, Parameterized Algorithms Computational Challenge, where there's like an annual contest with some implementations, but I don't think there's like anything like testing site for that. I mean, maybe some old challenges are available on Optil.io, which was the platform we used for the PACE, but I don't think there's anything like that.
It's called PACE.
Yeah, PACE challenge.
Okay, thanks.
Any more questions? That's then. Thanks, and see you next week for the next lecture on like preprocessing. There's preprocessing from the parameterized point of view next week. Thank you.
Thanks.